So Kay is going to present the solution.
So the question we have is the same as the example 2 in canonical transformation 1. So I'll just side by side so that it's easier for understanding. So last time you've mentioned to us not to use the exact same approach of the first type. So I chose the third type. That is this one, where you can see that Qj equals to minus round f. It follows as the same expressions as equation 26. So if we now look closer to the question, then we can just follow through. Well, first we find small q to express is the right-hand side of this equation. Then we find that the expression of Qj equals to minus round f3 round p is actually equals to that. So we can find f3 by solving the partial differential equation. So by solving the partial differential equation, we simply just add a constant, however, as an equation of big Q, because big Q now is not the variable being partial differentiated. So we now have the large f3, and we can find small p by the equation 26, where large p equals to round f3 round qi times minus 1. So we write it very simply, where now qi is equals to q, because we only have one pair of large pq and small pq. So now we just partial differentiate the equation with respect to q, and then we can obtain the expression where actually we make use of this equation in here. You can see that this expression of large p is actually this one. So if we make use of that, then we can find that the expression of GQ is given by p squared over 2 times exponential of minus q plus 1 plus q squared over 2 times exponential of q. So if we put back the GQ into the equation we've just found in here, then we can obtain the whole expression of f3. So for the sake of checking if the answer is correct, we can just refer back to the solution of using another approach, and we can find that the exponential q times the factor of 1 plus q squared over 2 is actually the same. So this is the solution of this question.
Any questions from the audience? So basically, I think you start with equation 14. Is it right?
Yes. This is equation 14.
Definition of capital Q and capital P, right? And then apply the relations related to the third type of generating functions.
Yes.
Now, I hope all of you will work it out by yourself at home once again, so that you can get a taste of how to determine the generating functions. Now, has any one of you tried to determine a generating function of type 2 or type 4? Is it possible? Is it possible?
I think it's possible, and the solution should be the same.
You mean F3 and equal to F4?
Yes. By guessing, because now we have F3 equals to F1. So it should be.
Okay. So I will try to, let's see, someone send us some chat message. So type 2, F equal to -1/4 P Q squared plus log Q. Wow, it's very complicated. 大全黑, do you hear me?
Hello.
Okay, can you show us how to get it? How do you get it?
I didn't write my steps.
Wow, you can see it right away.
I mean, I did, but I throw it away.
Oh, I see.
But
All right.
I just starting solving solving the equation.
Do you
That partial
follow
derivative.
the same ideas as K?
Yes.
Okay. All right. Thank you. So all of you can see that we can for simple examples, we can generate all different generating functions of different types. All right. But sometimes a certain type will be preferable or easier to get. Okay. All right. Let us move on and continue. We finished the exercise 1 last time. Now here is the exercise 2 and exercise 3. Now I give you 10 minutes to work it out, and I was ask some of you to present your answers. All right. Exercise 2 and exercise 3. 10 minutes. All right. 10 minutes. Exercise number 2. Is there anyone who would like to present your solution? Any volunteer? Exercise 2. All right. Hỏi Lần, can you try?
Yes, but because I'm writing on my laptop, so I'm using a mouse, so I only did part of it because it's very difficult to write with my mouse. So maybe I just show the proving of the canonical part. Is it okay?
Okay. Just
Okay,
try it.
It's just very simple. We consider actually there should be 3 conditions, right? Because you need to consider the P and P for different ij. Is it 0 and the Q? But since we are only talking about one particle, we can ignore these because I and j is equal. Then we only need to consider whether the result of Qi and Pj follow the delta ij, because again we are considering one particle, then delta 11 is equal to 1. So we need to show that this Poisson bracket equal to 1. Then we could just apply the formula given in the question. And then do this partial differentiation, and then you can find out do the partial differentiation, then you can see that u would equal to 1. So it should be a canonical transformation.
How do you do the differentiation of capital P?
So are you talking about the arctangent?
Right.
Then actually, if you remember, you recite the formula, then you can just use it. But if you haven't, then you could just write the tangent P would equal to let me see the question again. So tangent P should equal to minus Q over P, and then you do it that way, and then you just transform it back.
So you apply the implicit differentiation.
Yes, yes.
I see. So how about the generating function f1? Have you tried that?
I have tried that, but because I'm writing using a mouse, so I'm having a lot of trouble with it.
I see.
Yeah, so yeah.
Let me ask someone to help. Justin Choi.
Can you hear me?
Yes.
It might be very noisy because there's some construction near my home. I do it on paper, so I
Yeah,
cannot
that's
really
fine. Just upload it, right, to your PC or you can use your smartphone to take a photo.
Oh, okay. Wait a second.
All right.
Let me take that picture.
As I said, one of the final exam questions must be on generating function.
And then I share screen.
Okay.
Nah.
So you share the screen, take over the screen, and present your solution.
So I think
Yeah,
I forgot
that's
to
good.
prove the I think I forgot to prove whether the function is canonical or not. But then I calculate that by using I first find the p in terms of large Q and small q, equate that with round 1 round Q, and then by integration I find f1, which is q root 2 large Q minus half Q squared plus g of Q.
Yes.
And then I do something with large P, which is negative round f1 round large Q, and is equals to negative arctangent Q over P. So I also do the I use the f1 I found above, and then I partial differentiate with large Q, and then after the calculation I find g of Q being Q root 2 large Q, and then I plug this Q root 2 large Q back into the f1 equals blah 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 blah, and then I find f1 is 2q root 2 large Q minus half Q squared.
Okay. So your final answer is at the bottom.
Yes.
2 small q, 2 times small q times square root of 2 capital Q minus 1/2 small q squared. Am I correct?
Yes.
Now, if you differentiate it with respect to small q, what do you get?
I get 2 root 2 large Q minus Q.
So it's not the same as
No.
the expression in the third line. Can you go up round f1 round q? It's not the same.
It's not the same 喎。點解嘅？
So there must be something wrong.
There should be something wrong.
Am I correct?
But I think someone in chat was saying that my integration part has some problem. Which part? The G of Q1 or F11?
I think the F1 expression in terms of the integration is correct, but somehow you get it, you get some mistakes.
Maybe the G of Q part integration. Maybe maybe.
Can anyone help? 謝潘子峰, can you help?
I'm still working on that, but can you see that? Someone say that the square root 2q minus q squared cannot separate to square root 2q minus q. Yeah, I think that part is not correct.
So right. You cannot do that.
Oh, 係喎.
Wow. You need to be
No wonder.
careful.
No wonder everything is wrong.
In the final exam, you get 0.
Yeah.
So you have to be careful. All right. Can your fellow classmates help to answer this question? 朱海健, can you try? 朱漢健係咪？朱漢健 Can you try? Not here. 陳偉聰 Chen Wei Chong, are you there? Not here. 陳欣望
Not yet complete.
戴全希
Not yet complete.
鄧蘇清漢 are you there? 蘇清漢
No, I haven't finished it also.
麥海 McHowen Matthew Chan, can you try? Lin Ming Chun, can you try? All right. Okay. Let me show it to you then. Share screen. All right. Okay. So as shown by your fellow classmate, I start with the definition of small p and small q and small p and capital P, because the independent variables are the small q and capital Q, i.e. the old coordinate and new coordinate. All right. So I try to integrate equation 1 over small q. Okay. And here I put in the integration constant, which is an arbitrary function of capital Q. Then I define an angle theta in terms of the small q and capital Q as this. Then equation 3 can be rewritten as this. All right. So we integrate the cosine square theta over small q. then, making use of the definition of this sine function, we can make a change of variables and rewrite the integral in terms of theta. All right. Now the 2 cosine squared theta is equal to 1 plus cosine 2 theta. All right. This integral can be easily done, easily performed, and to give theta plus 1/2 sine 2 theta. All right. And then I try to express the results in terms of the small q and capital Q. In other words, we just go backward, all right? Reverse the definition, and here is the final expression in equation 4. Okay, so the generating function of type 1 involves the sine function and also this arbitrary function fq. The next step, I try to differentiate the generating function with respect to the capital Q. You have to be careful because it is quite a mass. So we differentiate the first term with respect to capital Q, and I get this, all right? And differentiate the second term, we get 2 terms. The first term involving the arcsine function. The second term, we get this. We obtain the second term by either looking up the tables of differentiation or by implicit differentiation, all right? And finally, the last term, df dq. And we can compare with with the given results, the rank F1, rank Q equal to minus capital P, all right? Now, here we just rearrange, collect the terms which can combine together, all right? These three terms, the first term and the second and the third term cancel out. This is an arcsine function. We can also change it to an arctangent function, all right? Because sine of some angle equal to q over 2 capital Q squared. It is the same as taking the arctangent function of this expression. Why do we do that? Because we can immediately write down the answer here, making use of equation 2. This is actually equal to minus capital P, right? Since rank F1, rank capital Q is equal to minus capital P, so dfq dq must vanish. In other words, fq is a constant. For simplicity, we can just take it as assume that it is equal to 0 without loss of generality. So as a result, the generating function is given by the arcsine function and also this part, all right, since fq equal to 0. Then we substitute in the definitions of capital P and small p, so we can write the generating function as given in equation, the last line of equation 7, minus capital Q times capital P plus 1/2 small q times small p. All right, so this is the generating function for for exercise 2. Then we will ask, will we be able to find a generating function of type 2? type 3 or type 4. All right. This is a good example for you because you can see that sometimes finding the generating function may not be so easy, may not be so simple. Say, for example, if we do not know how to integrate this part, then we get stuck, right? And sometimes we have to be using some tricky steps. For example, changing the arc sign to arctangent, right? In order to find this simple expression for the generating function. Okay. Now we have the third exercise, exercise 3. Prove that the transformation given in equation 28 is canonical and derive a generating function of type 1 or type 2. All right. Now, can anyone help us solve this problem?
I have finished the canonical proof, but I still haven't finished the generating function part.
Okay, try it. Show us
Okay.
how to do it. The first part. Oh, I stopped sharing the screen now. All right, go ahead.
Okay, so in this part to determine if the transformation is canonical is the same as trying to determine the Poisson bracket of large Q and large Q equals to 1. So in this part, we simply use the equation of tangent squared plus 1 equals to secant squared. So in here, we can just use the definition where round Q, round small q times round P, round small p, round large Q over round small p, and then round large P over round small q. So from this very rather tedious differentiation, then you can find out that a lot of terms can be crossed out. So it became a very easy expression where it becomes cosecant squared p minus cotangent squared p. So here, if you take a look where cotangent square plus 1 equals to cosecant square, then you can find that if we put the cotangent here, then you can obtain 1. So it's rather simple to get the canonical proof.
Yes.
However,
Go ahead.
and in type 1, I have solved till finding I haven't finished getting the GQ, but I guess the above is rather similar, where we have small p and large F1 over round Q, and these are the methods of solving the type 1.
That's right.
As requested by this question.
Right.
Yes. And then we have Q, E, the definition. So I have wasted some of my time trying to solve it by using this equation to begin with to solve for the Q, because to solve for the F1, because if we find P in terms of this equation, then you can easily find that the equation given is like this. However, if we do this,
Something wrong?
get a 0. And I very, very doubt myself, so that I use another definition to obtain Q, to obtain P for this equation.
Mhm.
And from this, we can just simply find the expression where we have the right-hand side obtained from the definition and the left-hand side from the equations of type 1.
Okay.
So if we solve it, we try to use trigonometry substitution so that we let sine u, because now we have 1 minus a thing square, we have to solve this. So it will be good if we have a sine or cosine.
Okay.
So I chose sine because I don't want the negative sign.
Hmm.
So here I have sine function let to be like this. In this case, I just let the q to be a constant. So this it is for the integration, because integration doesn't have the differentiation thing where you have another constant and it's dependent. So I just do a very simple integration where you use double angle formula and get a very complicated form. But after simplification, you can get things like this. Oh, you can get things like this. However, I've reached this part, yeah, and I haven't done it yet.
I see. Okay. Now, can someone help finish this? Samson, can you try?
No, I'm still doing.
I see. Diệp Trạc Hy. Diệp Trạc Hy.曾俊偉.曾俊偉. No one wants to try. Lâm Minh Trân. No. Okay. Perhaps I just show you the answer. I try to obtain the the generating function of first type. All right. You can also try to derive the second type. Now, the small p, since I'm going to generate, I'm going to find the first type. So the independent variables are the O coordinate and U coordinate. So the small q and capital Q. So I express the small p and capital P in terms of the O and U coordinates, as shown in equation 8 and 9.
The screen sharing is not on yet.
Oh, I see. Thank you. Oh, can you see it now? All right. So I just put in I just write down the definitions of the O momentum and U momentum in terms of the O coordinate and U coordinate, as shown in equation 8 and equation 9. To begin with, I integrate equation 9 over capital Q. And this FQ is an arbitrary function, which is basically the integration constant. So I let x equal to the integrand. Okay, x equal to the integrand. Then equation 10 can be rewritten as this. All right, the integrand, by a change of variable, the integral will be rewritten as this. Now this integral can be performed easily. The first part here gives you x. The second part gives you the arctangent. If you don't remember this, just look up the tables of integrals, or you can perform this integral by substitution, right? By substitution. Let let x over q equal to the tangent of some angle, then 1 plus tangent of the angle square will give you the secant square. All right. So it is a standard approach. Then I put back the definition of x. So I substitute the definition of x back to this expression. Then the second term is given by us, and the third term is given by us. So we have the f1 given in equation 11. What we need to do now is to determine this arbitrary function q. So we differentiate this f1 with respect to small q. We have the first term and the second term. All right. Now, there are two terms coming from the third one here by definition. All right. One of it simply cancel this out. In other words, we differentiate this arctangent, we'll get a result which cancel this. All right. So we're left with this one only. And we put back the definitions for the P here. All right. Here. Then we realize that this is the cotangent small p. Cotangent small p is equal to the tangent of pi over 2 minus p. In other words, this arctangent of this tangent function will give you the angle, the argument. All right. So we have dfq dq equal to pi over 2. So the arbitrary function is a linear function of q with the prefactor pi over 2. So our final answer is this. The generating function of first type f1 is equal to pi over q plus pi over 2 times q plus this term and also this term. All right. So there are 3 terms to it. And then we realize this arctangent is equal to pi over 2 minus p. Okay. We just put back the definitions from above. Okay. From here. Then combining the first term and also the second term, we are left with small p times small q. And the small p is given by this sine function, all right? Arcsine function. Combining these two, rewriting the arcsine function, we will have the capital P plus small q times small p. All right. So that is our final answer. Now, this final answer is deceiving. Why? Remember that the generating function of the first type is a function of 2 independent variables, namely the small q and capital Q. All right. However, this the simple answer in equation 14 is in terms of capital P and small p, both of which are functions of small q and capital Q. All right. So in fact, it is not not as simple as we think. However, if we represent the f1 generating function in terms of the dependent variables, then the expression is much simpler. Okay, so this is the solution for exercise 3. Now, I hope that you will help, or I will put it as part of the next problem set to find the generating function of type 2 for this problem. All right. Okay. Any questions about the solution? Any questions? Now you can see that yes, I will upload this PDF. Don't worry. I will upload the answer here. I give you all the details because I know that I will give one question on finding generating function in the final exam. In fact, finding this generating function is not as easy as you think. All right. Can you see it now? It is not as easy as you think. That's why the theorem is powerful, because you don't have to go through all these calculations. What you need to do is to compare the fundamental Poisson brackets of the new set of the sets of compare the Poisson brackets of the old conjugate variables and also the new conjugate variables. Right. Okay, any questions? If not, then I will give you another example. Here. Show that the following transformation is canonical. All right. Now this time we have a two-dimensional problem. Okay. Here alpha is some fixed parameter. Apply this transformation to the problem of a particle of charge Q moving in a plane that is perpendicular to a constant uniform magnetic field. Express the Hamiltonian for this problem in terms of the QP, capital Q, capital P coordinates, letting the parameter alpha take the form given in equation 2. From this Hamiltonian, determine the trajectory of the particle. I believe that all of you are familiar with this example. When we have a charged particle moving in a plane perpendicular to the uniform magnetic field, the trajectory is a circle. All right. So it is a well-known problem. So to prove that the transformation is canonical, we try to derive a generating function. Okay. Now we let us work on deriving a generating function of the first type, which is a function of the old and new coordinates. Right. So the px, small px, is equal to round f round small x, round f round x. Capital P1 is equal to minus round f round q, capital Q1. Small py is equal to round f round y, and capital P2 is equal to minus round f round q2. Okay. Now, in terms of the coordinates, the momentum, all the momentum are given by these expressions in equation 4. Okay. Now, this is the definitions for the transformation x, y in terms of the new coordinates and new momenta, px, py, expressed in terms of the new coordinates and new momenta. Right? Since all the coordinates are independent variables, so all the momenta are dependent variables or functions of the coordinates, as shown in equation 4. Now, you need to be careful when you try to figure out the definitions of all these momenta. All right, just be careful because they involve some trigonometric functions. So we first integrate round x over x. So we integrate this over x. All right. Since y is independent of x and q2 is independent of x, so this integral is simple. It just gives you a linear function of x, right? And also the integration constant, which is an arbitrary function of small y, capital Q1, and capital Q2. Then we go back to equation 3. We know that we can differentiate this generating function with respect to y to give the py. All right. So we differentiate this generating function with respect to y. So the first term gives you alpha squared over 2 times x. The second term will give you round f round y, right? And we know that py is equal to alpha squared over 2 times x minus alpha times alpha y minus q2 times tangent q1 is shown here. Okay, it's shown here. This is py. So we compare both sides of equation 6 and we obtain round f round y equal to minus alpha times alpha y minus capital Q2 times tangent capital 1, capital Q1. Then we integrate this equation, or integrate this equation over y, or we find the antiderivative of this derivative. Okay, so the f can be expressed as minus ay times 1/2 alpha y minus q2 tangent q1 plus an integration constant, which is an arbitrary function of capital Q1 and capital Q2. So once again, we differentiate this the f with respect to capital Q2 to obtain the capital P2. All right, the capital F is given by this, and also this function f. All right. Straightforward differentiation will give us alpha x minus alpha y times tangent capital Q1 minus round g round Q2, capital Q2. And according to the definition given here, so we know the capital P2 is equal to alpha x minus alpha y tangent capital Q1 plus Q2 times tangent capital Q1. All right. So we compare both sides of the equation 9. We realize that round g round Q2 is equal to minus Q2 tangent Q1. The integral is straightforward. Okay, the antiderivative is straightforward. To give g equal to minus 1/2 Q2 squared tangent capital Q1 plus the integration constant, right, which is an arbitrary function of Q1. Finally, we differentiate the f with respect to capital Q1 to give you the capital P1, right? And this differentiation will give us this, all right? And by definition, the capital P1 is this. So compare these two expressions, we realize that the dHdq1 equal to 0. In other words, h is a constant. And we are free to choose c equal to 0, okay, with our laws of generality. So as a result, we obtain the generating function. It is given in equation 13 here. Looks very complicated, all right? By definition, the B field can be expressed in terms of some vector potential, the curl of some vector potential, as shown here. The B field is equal to curl of a vector potential. And this vector potential is given by this, okay? We are using the circular gauge. Then the corresponding Hamiltonian is given by small p minus the charge. This is the charge, okay? Divided by c times this vector potential altogether squared, all right? we just plug in the definitions of this vector potential to the expression, and finally we get a simple expression, a nice expression for the Hamiltonian in equation 15. Here we have put alpha equal to square root of QP naught divided by C. Now this Hamiltonian is now expressed in terms of the old coordinates and old momenta. Now we want to rewrite it in terms of the new coordinates and new momenta, right? So we make use of the definitions shown above. We realize that, wow, how nice. It turns out that the Hamiltonian is proportional to the capital P1. Okay? So it is clear that capital Q2, capital P1, and P2 are all constant, while the equation of motion for Q1 is equal to this. Okay? Because the Poisson bracket between Q1 and H will give you omega c, all right? So all the others are constants. Now, once we get a Q1, then we can invert the definitions to obtain the old coordinates and old momenta in terms of the time. We can rewrite them as a function of time. So this is the solution of the given problem. As you can see, x, y indicate the coordinates x, y indicate that the motion of the particle is a circular motion, okay? And the path, the trajectory of the particle is a circular path, or is a circle. And the corresponding momenta are given here in equation 20 and 21. And we can see that the momenta are oscillating sinusoidally, all right? So this is the solution for this example. I will upload it to the web page as well, course web page as well. Okay. Now you can see that if we have a good canonical transformation, the problem will become very simple, and we can obtain the solutions easily. After obtaining the solutions, we can reverse the transformations and obtain the solutions in terms of the original coordinates. All right? Any questions up till now about this problem? So in your common homework, the questions will cover the generating functions and canonical transformations. So you have to work out the details. Any questions up to now? Okay, now it is your turn. See? Only one. So, okay. I thought I have a few more examples. Let me double check. Additional examples. Yes. All right. So this is your turn. Now, show that the following transformation is canonical by determining a suitable generating function of the transformation. Now, if you are allowed to make use of the theorem, it is much easier. We just we just investigate the Poisson bracket between capital Q and capital P to see whether it is equal to 1, right? However, you are not allowed to do so in this example. You are required to find a suitable generating function. Okay. All right. Let's see. This problem can be solved easily. All right. 5 more minutes. Can you go ahead and try it? 5 more minutes. Finding. Okay. Give you some hints. Find a generating function of type 3. All right. As you can see here, so I express small q and capital P as function of capital Q and small p, all right? So I expect you to find a generating function of type 3, okay?
Of type 3, then we first consider the as given the definition of P and Q. Now, if small p and small q are expressed, if large P is expressed in terms of small q, where q is defined in as this equation, then we substitute it to get the large P.
Yes.
So now I've highlighted the words for type 3 in blue. So to have f by the integration using this equation, then we can integrate it with respect to P. If we integrate with respect to P, then we know that the tangent is equal to secant squared. So we treat the large Q here as a constant where it can be pulled out as a factor. So here we have the tangent as mentioned, and we add a constant term where the constant term is a function of Q. Then we use the method of type 3 to determine by determination of large P, we can find the G of Q, hopefully. So here we try to differentiate large f with respect to large q. During the differentiation, we can find that if we differentiate this by the chain rule, then we pull the power down, and we have 2eq minus 1. And 2eq minus 1, we chain rule, we need to differentiate eq, so we times eq, because differentiation of eq equals to eq. So, and we treat this as a constant, and we copy it right here. Then we try to differentiate this as well. However, by definition of what we defined large P is, we find that these two terms is actually the same. This means that the g prime of q equals to 0, which implies that the gq is actually a constant. So without determining the constant, the whole form of the generating function will be in this form.
You all agree? You all agree? Hỏi Lun.
Yes, but I think the k can be reduced because we have the freedom to choose k. Then if I were k, then I would choose k equal to 0.
You choose k equal to 0.
Yeah, because k is arbitrary.
All right. Okay, 大全希. Can you can you tell us your questions?
After she gets the g of q is equal to k, she then substitute it in the wrong equation, I guess. I mean,
Okay, which one?
She substitute it back to p instead of f.
Yes. Am I correct? There's something wrong here.
Oh,
Yeah.
oh, right. Oh, right. I saw it wrong.
Okay.
I didn't check it.
Hmm.
It should be.
Now, this is my advice. Once you get the solution, differentiate this generating function with respect to small p and also capital Q to see whether you can get back the answers. If you cannot, then there must be something wrong. Am I correct?
Yes.
So it's a good way to check it. All right, thank you very much. Can I get back the screen?
Thank you.
Now, let me show you my answer then. It is exactly the same as what K presents. So we integrate the Q over P. Then we get a nice results in equation 3, all right? And then we differentiate with respect to capital Q will give us minus capital P. So we have this and compare both sides of the equation. It tells us that the FQ equal to 0 for simplicity. Now this is F3, okay? Keep this in mind, this F3. The full generating function is given by F3 plus QP. Don't forget, okay? Don't forget. In the final exam or in your homework, you have to put back the additional part for generating function of type 3, type 4. Okay? So this is the full answer. Okay? All right, so I'll stop here today. And remember that next week, we change back to face-to-face teaching mode. And I hope that all of you will come and attend the lectures. And during the lectures, I will use a pen and whiteboard very much. so that when you have answers, we can communicate much better. Okay. Okay, so I see you next week. Any more questions? One. Any more questions? Twice. Oh,
I have a question.
Good.
So the whole purpose of the generating function is if it's giving us a method to simplify the Hamiltonian, right?
yes,
But
yes,
so
yes.
are we so far doing the questions that the transformation is already given? So so I mean, why the exercise we so far doing the transformation are given instead of we finding it out?
I don't quite get it. Do you mean that we know the transformations already at the very beginning, am I right?
Yes.
But we do not know whether it is canonical or not. So we have to figure out the generating function. If we can find a generating function, then we know that the transformation is canonical. Can you see the point?
I see. But how is the transformation are found in the first place?
This is a good question. So you have to think out, you have to find a suitable transformation. Okay? Just like a coordinate transformation. Because we know the well-known transformations, like from Cartesian coordinates to spherical coordinates or to cylindrical coordinates, right? But there are other coordinates. Do you know that? Like parabolic, elliptical. So there are different types of transformations. And you may also propose some new types of transformations, which may help simplify the problems. So you're free to construct suitable transformations for different problems. For example, the proposed transformation here, given in equation 1, may not be it is a good transformation for a certain problem, but it may not be a good transformation for another type of problems. Can you follow me? So for different types of problems, you have to find the corresponding suitable transformations. And how to construct the transformations requires a lot of experience. Okay? Similarly, when you study quantum physics, all of us know that unitary transformations are suitable unitary transformations can help simplify the given problems dramatically and make it simple. All right? So you have to construct the suitable transformations by trial and error, making use of your intuition and experience. All right? But after proposing a transformation, you have to double check whether it is a canonical transformation or not. Either determining a suitable generating function or applying the theorem. Okay?
So the point of
Yes.
So the point of using a canonical transformation is after the transformation, the Hamiltonian should be simple, and furthermore, because this is canonical, so the form of the Hamiltonian equation, the form keeps the same. It keeps the same form, and
Like
so
the physics remain the same.
okay. So and then so that it can be easily evaluate or calculate whatever.
Right.
Okay.
Right. Actually, we like to map a problem, a difficult problem, via a suitable canonical transformation back to some problems or some systems which we are familiar with. Say, for example, if we can map a complicated problem back to a simple harmonic oscillator problem or a free particle problem, we know the answer right away without doing a lot of mathematics. Am I right? We can write down the solution right away. And then, after obtaining the solutions, we reverse the mapping, reverse the transformation, and express the solution in terms of the old coordinates and old momenta. Most of the time, after the reverse transformation, you will find that the solutions are so complicated, which cannot be done, cannot be solved, cannot be determined easily. Okay? So this is my advice for you, especially for those who are interested in pursuing physics research. Whenever you encounter some new problems or some new equations, differential equations, partial differential equations, or some integrals you need to solve. First of all, think about if you can reduce or map those given equations, given integrals, back to some familiar ones by suitable substitutions or change of variables. All right? Say for example, for an integral, the integral may be very complicated, and a commonly used technique is integration by parts. But it is very tedious, and sometimes it does not lead us to a desirable end. However, if one knows a suitable substitution, then the integral can be done easily. All right, after the change of variables. Same for equations, differential equations and partial differential equations. Complicated partial differential equations can be reduced to a very simple one if you can identify a suitable change of coordinates, change of variables. All right? All right, in lecture 19, why do we define type 2 generating functions as such? Why is there a QP term? This is the question from Wang Hunzhen. Okay. Now, I'm not going to tell you the reasons behind it. It's too complicated for you. So I'm giving you the recipe. Okay, type 1, type 2, type 3, type 4, purposefully. Now you will ask, why is it so? Why is it so? Then I would suggest you to read Goldstein's textbook on classical mechanics. All right? Goldstein's classical mechanics. Now, if you don't add to these two terms, all these extra terms, then those partial derivatives of the generating function will not be so simple. All right, that is a simple argument. All right, so you need to add those extra terms so that the partial derivatives of the generating function or part of the full generating function look very simple. Okay, can be handled easily. All right. Okay, any more questions? Besides Goldstein's textbooks on classical mechanics, which is a thick one, okay, which is a very thick one, you can also go to a very thin one, very, very thin. You are surprised to see a textbook on classical mechanics to be so thin. This is the textbook by Landau and Lifshitz. Okay, by Landau. Classical Mechanics by a Russian physicist, theoretical physicist, Landau, David by Landau. Now, Landau is commonly known as the poet in physics. Commonly known as a poet in physics. You know the difference between poem and an essay. All right, poem, precise and concise. An essay, it can be very long, but also concise, precise. All right. Okay. Anyway, any more questions? If no, then we will end this meeting now. Yeah, Landau and Lifshitz.
May I ask?
Yes. Go ahead. Lifshitz.
Okay.
They are Russian physicists.
Okay.
Right? You can find it in the library. Very thin. Covers all the materials. Okay. Any more questions?
May I also? Did you mention the? I forgot how to even pronounce the name. The ghosting.
Goldstein. Goldstein.
Oh, I see. Thank you.
It's a thick book, and it has a very detailed discussion on canonical transformation. All right. Okay. Now, so I will see you next week at the lecture halls. All right.